Um, this is a tutorial in Grasshopper, and we're going to talk about um, vectors and frames. We want to do a practice assignment together, step by step, and try to use the new components that we learned via the tutorials that we saw, using vectors, planes, and frames. So to get started, I want to start with adding a couple of points in Rhino viewport in order to create a curve, NURBS curve from these points. And these points are going to be the control points with which I'm going to parametrically control my curve. So if I just assign the points into Grasshopper, you'll see they get green selected. Then the next step would be to create NURBS curves, and we assign the points to the vertices input from NURBS. One moment, I'm actually going to change my Grasshopper preview into showing icons and also show draw full names. Yeah, this is more clear right now. All right. So if you see right now, you can actually move the location of every point, and there you go, the curve change. You can make it a wave, you can make it any shape you want, an arch, whatever. So going back to Grasshopper, what I want to do today is to make a cool effect appearing around this parametric curve that we made. I want to explain more clearly what we want to do. Is if I go here in the Photoshop, I can explain better. For example, this is our curve, and what I want to do is that I want to create this effect, the wavy effect around it, on both sides, something like this. Oh, horrible drawing, sorry. And the same effect actually in 3D, so it will be on top and bottom, but let's assume this is the shape. And the way we do it is to have this curve divided into several points that we will move later along a vector to regenerate a new curve, which is the wavy one. So we would have to move our points towards these directions, the vectors, and then make the new curve from them. But how are we going to create these vectors? The best way is to generate perpendicular planes in our curve within these given subdivision points, and from the planes, which every plane has an origin, which could be these points, and x, y, and z directions. So we can extract these x, y, and z directions as vectors and then use those for moving our points. This could be, for example, the x vector. If this is x, this is y, and this is z. And we have to move it plus and minus the negative value of x in order to get this mirrored effect. So going back to Rhino again, we are going to do it step by step. This is the curve we want, and if I want to subdivide it into multiple points, there is the component divide curve. I can already use divide curve, and all I have to give it is the number of subdivisions, which here is number 10, or there is another component which is called divide length, which would divide my curve based on a given length. For example, I want my curve to be divided with the distances of 4 millimeter. So then if I check it out, every single distance between these 2 points, the subdivided points will be 4 millimeter. If I decrease it, there will be more points. If I increase it, there will be less points, obviously. But either we choose any method to subdivide the curve. I would stick to just a normal divide curve, and I want it to be divided by number 20, which means 20 points here. Well, actually, we will get 21 because it's a list of points starting from item number 0 to item number 20. Therefore, we will have 21 items in this list. If I grab a panel, then you can see how this list looks like from the point number 0 to the point number 20. So what we wanted to do is to create perpendicular planes at these points, the planes that are perpendicular to our curve. And if you double click on the canvas, then you can type P, which is standing for perpendicular, frames, or P frame. If I click on P frame, this is the component that creates a perpendicular plane to the curve. So I have to give my curve as the input here, but then it wants to know at which parameters, or basically at which locations on the curve it wants to give us the planes. That's the reason we subdivided the curve into these points, so that we can use these parameters. So I'll just give this output parameters here to the input parameters to the perpendicular frames, and there you go. This is our generated perpendicular planes on the curve. So if I zoom in, then you would see, as I explained here, every plane has x direction, y direction, and the z direction, which will be the normal vector of the plane, is alongside the tangency on this curve. I'm going to visualize it better so that we would understand how these vectors are on these planes. But first, in order to extract those vectors, I would have to deconstruct my plane. There's a component, if you just double click on canvas, you can use it. Deconstruct plane. It would extract all these information from the plane, which is origin point, x-axis, y, and z-axis. So if I want to actually now visualize the vector directions, I would preview off my planes here, and I will go to the tab Display and Vector Display. This is the component that visualizes the vectors. You'll give any wanted desired vector you want to be visualized here, and then the origin point. So if I zoom in, then you would see it displays all single vectors that are along the x-axis from these points. If I just do the same in order to see what would be the y vector, then I'll just have to copy paste it and give y as the input. And also the same I'm going to do with z to check it out. And as you see, the z is actually following the tangency of the curve. It's clear, right? This way. It looks like a plane on these points that is perpendicular on the curve. And if I just happen to drag one of these points away again to change the shape of my curve, it will be always updated because it's parametric. So going back to this, if you remember, now we want to move our points along these vectors and also the opposite direction, which would be the negative vector. So we have the first vector, which is x, and I want to move the point along x by, for example, 10 centimeters, 10 millimeters. So if I just grab the component move and 10 as the given number, then I'll just have to connect origin, which is the point, to the geometry, and then the same vector that I want to move multiplied by the number that I want to move the points. The result should go to motion. So then you can see how I'm moving these points away from the curve following the axis of x. Beautiful. So now we have to do the same for the opposite direction as well, if you remember, because we want these points to be also on the other side. And for that, I can just copy paste here this result, and I would multiply it by this component called negative. So I would calculate the negative value of this, and then I can hold shift and connect it again to the motion. But you see here on the viewport in Rhino that actually this is not the effect we wanted. And the reason why for that is very simple. It's because at every list we want to move 21 points, but here, as you check, for example, the input here, there are 21 points that should be moved with 21 different vectors, but here instead of 21 we have 42. That's because we given the moving factor from the positive vector and the negative, which was also another 21 vectors, into the same input. So this problem would be fixed if we can manage to assign these two lists separately. In order to do that, I can just merge them into one list externally and create a partition within the list. So if I just type partition again, partition list, this will be the component that I can give, hey, I want my list to be subdivided within partitions that each of them have, for example, 21 items in. So the same list here that has 42 will be our list, and the size is the same size of our list. So this component list length would extract the size of the list, which is 21, and 21 would be the given size for the partition. The chunks output is two lists that each of them have 21 items in. So if I connect this to the motion, our problem is solved. Bingo. So now I have two different lists within the move that if I want to generate a new NURBS curve, it will be as easy as just connecting the output from move to NURBS. And then it seems like we have offset curves made from our initial profile curve. And if I just play around with these numbers, well, then I can offset them at a different distance. Well, to just be a bit more simple here, I'll just connect one input to both. So I can offset them on both directions within the same value. But if we go back to our drawing here, this result in the Rhino, our script, is actually not the same as this wave. And in order to do this effect, the wave, sine wave-like effect, we have to give different values to the points for moving. Here we are giving just one value, which is 2, and if we just change this, you would see that the distance of the points will be changing according to this number. But if I want it to be different like this, it means that, for example, the first point should move 0, the second point should move, for example, 5, and then again the third 0, fourth 5, and so on. So if I want to make this, I have to add these inputs, for example 0, 5, 0, 5, and repeat it along this whole curve. So I would add another number here, for example 0, and going back to Grasshopper, yeah, and 2 and 0 would be the sequence that I want to repeat and give it into the moving component to move my points in a sequential manner. So if I want to create a data out of these two inputs, then I would have 2 and 0, and I want to repeat this data along the curve. In order to do that, I have to know how many points I have in that curve to repeat this list based on the number of points. So I have extracted that information before, where I wanted to give it to the size of the partitions, if you remember. Then I can just use that output, which was the list length, as the length of the data I want to, the list I want to repeat my data. And if I now check it out, the output, I would have this data 2, 0 repeated 21 times throughout my curve. So I would have 2, 0, 2, 0, 2, 0, and so on. And that will be what I need in order to create my wave. This repeated sequence of data is what we need to create our curve, the wave curve. I'm going to select and move these components a bit ahead so we would have some space. Yeah, so instead of these fixed numbers, I'm going to replace them with the repeated data and watch what happens. You will see that the wave happens, right? And I can then like increase this number to create more sharp curvature. And the second number could be even set to negative, so that, for example, you see they can even intersect or pass through each other, and making these type of effects. And the same thing that we want to do with y direction. So here's our script that we made already. We can copy paste it, and instead of x, replace the vector with y. So if I just grab this output to yeah, here and here, we should see that the same thing happening in the y direction as well. I'm going to turn off the preview of the moved points so it will be more clean, the viewport. And yeah, this is exactly what we wanted to make. Oh, in order to make it more interesting, you can also add more numbers on the way. So for example, I want to add 0 and 5 also. So that I would have 5 to 0 and 3 to -3, and then go on. So I would have more control over changing this curvature. So the next step is to, I want to make these lines, the generated curves, into 3D pipe-like shapes. So I have to create a section for them. If, for example, each of those curves taken out here, I want to make him into a pipe, like a 3D object. And the way to do it is to create a section, for example, a circle is one of the simplest ways, and have those circles again perpendicular and parallel, so that I can run the command loft and make a pipe out of all these circle sections. And then later I can change the radius of these circles and adjust and control the thickness of this pipe. So here's, for example, the curve number 1. I'm going to test it on that one. I would have to again subdivide my curve into a number of points. I'm going to actually choose a very high number, like 200, so that I would have a good resolution. And here you see, for example, the both curves are subdivided into 200 points. And from these points, I want to make perpendicular circles. So I just type circle. This orange component is the one that makes a circle in Grasshopper. If I give points as the planes here, you'll see that it makes us 200 circles that we can also adjust the radius, for example 0.4 or whatever. And these circles are what we are going to use as sections. But if you look closely, you see the problem is that they are not actually oriented as they should be. They should be perpendicular to my curve, but then it seems they're all parallel to each other, and they're parallel to the ground, which is the XY plane. Well, that's because if I check out the planes by default on the circle, as you see, it uses world XY plane, and that's why it's all parallel to the ground in the Rhino, which is this plane. So I have to give it a different plane if I want it to be oriented into a different orientation or direction. So it seems like we have to repeat the same function that we did before, creating here perpendicular planes, because those were the planes that we created, and based on the normal that were parallel to the tangency of the curve. That's how you create perpendicular planes. And I'll just type p-frame again. I would assign my curves into the p-frame, and the parameter is again the same. And now we have all the planes perpendicular to the curve origin at these points. Well, I don't need to see the frames, so I can preview it off. But then these frames are the input for the plane for the circles. If I give it to the component circle, then you will see that all these circles that are made on the curve are the ones that are actually perpendicular to the curves. These are the sections we would need. And if I check the output here, I would have two lists of curves, two lists of circles in which there are 201 circles. So I would have to run the command loft to create the pipe from the circles, and this is the result. I can later change the radius of these pipes, as you can see, and also copy paste the same script for the Y and just change the inputs, and then I would have this 3D shape that I can control at any point, at any time, with the different parameters. For example, if I want to drag these points. And also again change the radius of the pipes. I would also preview of the circles because we don't need to see them. And here we have this geometry made. You can then select them, or you can just assign them into one component so that we can bake it all in at once, group them, and here it is, it's in the Rhino. Well, this is it. This is the assignment, the exercise we wanted to do together, and hope you guys found it actually useful. There's a lot we can do with these components, like with the functions of vectors and planes and frames, to play around and create different geometries and shapes. I mean, this was something that we did with actually curves, subdividing it into a number of points that we use those points to create planes, and then move the points and regenerate new wave curves out of it. Imagine that you can later do the same process on a surface. For example, you can create a surface, subdivide it into a number of points, and again extract planes from those points, and then move the points in different directions and recreate a surface that will look way more different, like a wavy or completely different shapes from the original surface. It's up to you. I mean, you can use your creativity and explore different shapes that you can create from playing with vector and planes.